Yeah, so let's move on to the next topic, which is Fourier transform of periodic signals. Okay, so let's say let x of t be a periodic signal. Okay, so x of t be a periodic signal with period capital T. Okay, so with period capital T. So what do I mean by this? We mean that x of t plus capital T equal to x of t. Okay, so as x of t is a periodic signal, so it will have Fourier series representation, and let it Fourier coefficients be ak. Okay, we'll write down as x of t is periodic. Okay, as x of t is periodic, and let's assume that it satisfies all the Dirichlet conditions. Okay, as x of t is periodic, it will sorry, it will have it will have Fourier series representation. When I say Fourier series, we talk about exponential, okay, not trigonometric. So it will have Fourier series representation, okay, Fourier series representation. And how does that look? X of t equal to summation k equal to minus infinity to infinity ak multiplied with e power plus jk omega naught t. So this is the Fourier series representation. Okay, and what do we call about ak? Where ak's are Fourier series coefficients. Okay, we know this how to find out them. Fourier series coefficients. Okay, so let's assume that we know the Fourier series coefficients. Okay, now question is, how do you find the Fourier transform of x of t? Okay, so how do we start? We start with this. We know that uh, CTFT of e power jk omega naught t is how much here? So which property we have to use? We have to use shifting in frequency domain. So this should be 2 pi times delta of omega minus k omega naught. So we will use this note, and we try to find out the Fourier transform of x of t. So this implies x of j omega. So x of t is this signal. So that fellow's Fourier transform would be how much? Because Fourier transform is linear, ak is a constant. So what will happen? You will get summation k equal to minus infinity to infinity ak. So just now we have seen that e power jk omega naught will have 2 pi times delta of omega minus k omega naught as the Fourier transform. So this fellow will have 2 pi times delta of omega minus k omega naught as the Fourier transform. Means what? Fourier transform of a periodic signal is what? It's a linear combination of shifted Dirac delta functions. And where do the Dirac delta function exist? It exists at integer multiples of fundamental frequency. Okay, so we'll write down that. So this implies x of j omega. Okay, x of j omega, Fourier transform of this signal is what? It is linear combination, correct? So it is a linear combination of what? Linear combination of shifted Dirac delta functions. Linear combination of shifted Dirac delta functions. And where are they located? Shifted Dirac delta functions located at what? Integer multiples of fundamental frequency. So integer multiples of fundamental frequency, which is omega naught. Okay, and the coefficients are, once I say linear combination, coefficients will come into the picture, and coefficients are nothing but Fourier series coefficients. The coefficients of linear combination, the coefficients of linear combination would be, okay, so coefficients of linear combination would be exponential Fourier series coefficients. Okay, exponential Fourier series coefficient. So this is just for a note. Okay, so what do we say? We say that Fourier transform of a periodic signal is linear combination of shifted Dirac delta functions. And where are they located? They are located at integer multiples of omega naught. Okay, so let us summarize what we have got. So we have got a periodic signal x of t whose Fourier series representation is given by summation k equal to minus infinity to infinity a k e power j k omega naught t. So this fellow will have what as Fourier transform? That fellow will have x of j omega, which is equal to summation k equal to minus infinity to infinity a k times 2 pi delta of omega minus k omega naught. Okay, so that is what we have got. This 2 pi you can bring it out because it is a scaling factor. Okay,